G'day chemistry students. In this video we're going to be covering dot points 3.3.1, 2 and 3, which are all of our dot points under this idea of collision theory. Today's aim is to introduce some of those core fundamental concepts so that we can spend the last couple of weeks of class doing some practicals looking at how we can affect reaction rate in a bunch of different reactions. Let's get into it. So first off, what I want to talk about is the idea that particles that are reacting together have to collide and come into contact in some way, shape, or form for a reaction to occur. However, something that's really important to understand is that when collisions happen, not all of them will result in a chemical reaction, which explains why in a lot of cases, chemical reactions do not actually proceed even if you put all of the reactants together. They might be able to interact, they might be able to collide, but that does not mean that a chemical reaction will occur. And there's a couple of reasons for this. First off, our reactants may be moving too slowly. So when they collide, they do not have enough energy for an actual chemical process to occur. They just bounce off each other, essentially. The other factor that we need to focus on is whether or not the collision is happening in the right way. So what that means is sometimes, not all the time, but sometimes chemicals have to collide in exactly the right spot so that specific parts of each molecule come into contact with each other. And if that happens, then a reaction can occur. This can be a little bit tricky at times, depending on how easy it is to access the reacting part of the chemical. So that will also have an impact on whether or not a chemical reaction will occur. However, if you have a collision in which there is enough energy and the particles are arranged in the right way to collide in the right spot, then you will have a chemical reaction that occurs. So to take that a little bit further, the two factors which we care about the most that influence reactions: the number of oriented collisions. So first off, if we just have more collisions in a reaction, so more particles present to collide, so less versus more here, this side with the more particles will mean that there are more collisions, which means that it's more likely that a successful collision will occur in which the chemical reaction proceeds. So if we're looking at the number of oriented collisions here, in particular, more particles means more collisions means more reactions. And that's a factor which can influence a reaction or its rate. To build on that as well, if we have a higher surface area of particles, what that means is there are more surfaces in which collisions can happen, which again will increase the number of oriented collisions, and as a result, increase the number of reactions that are happening in a really short amount of time. However, the number of oriented collisions is not the only factor. We also need to focus on the energy that the collisions have, and this idea is activation energy. So we can use energy graphs like this. So usually we have time on the axis down the bottom, even though that's not labeled, and energy on the side axis or the y-axis. And in all reactions, there will be some sort of energy requirement that the particles that are colliding must meet for the reaction to actually proceed. So in this example, reaction A requires more energy when the particles collide compared to reaction B for that reaction to actually proceed. So if you had a collision that had an energy level, say where my marker is now, that would probably mean that reaction A wouldn't proceed. But if there was a collision with the reagent in reaction B, then if they had that amount of energy, then that reaction would probably proceed. And this all affects this reaction rate, which I keep talking about. And so again, a term that's coming up for the first time in specifics in our syllabus. We have talked about it a little bit before in previous modules, but here is where I'm going to be giving a formal definition of reaction rate. Now, to keep it really simple, it's the speed of a chemical reaction, how fast the reaction is actually proceeding, which could be interpreted as, if we start talking about collision theory, the number of successful collisions that happen in a second or any other unit of time. And even more specifically then, the change in N over time. So if we have reagents or reactants turning into products, we're looking at how quickly the number of moles of reagents are declining over time. So for fast reactions, the number of reagents will drop quite quickly, and in slow reactions, the number of moles of reagents will drop much slower. This can be shown in a graph that may look like this. So concentration being on the y-axis, concentration is just an extension of N, so you could have number of moles or concentration here. They both really do mean very similar things, and we see the progress of a reaction over time. So at the beginning here in this process, what we see is that there is a faster reaction rate because the concentration of the reagent and the products are decreasing and increasing respectively quite quickly in a large amount over a short amount of time. But compare that towards the end of the reaction, the products and reagent aren't changing in their concentration very much over much longer periods of time, meaning that there is a slower or smaller reaction rate at the end. Thank you very much, everyone. Hopefully that covers some of the basics. We'll be spending a lesson talking about some of those concepts, making sure that we're all on the same page as we move into a series of lessons in which we're going to be doing experiments, looking at how reaction rates can be changed using specific factors. So in the first experiment, what we're going to be doing is changing reaction rate through temperature. We're also going to be looking at a few other factors. Some of them are outlined in this video here. But until then, have a good one.